Right. And we're live. Hello everyone, how's your Friday going? Hello, welcome to the stream. All right, getting set up here and then we'll get started. How's everyone's Friday going so far? Let us know in chat. All right, let me just make sure I get all of my terminals set up and everything so that we can get started. Hello, Samara. Welcome back to the stream. All right. So let me we actually have even newer profiling data. We might just pull that up real quick. For those who didn't already see, we actually already dropped some profiling data into the tweets for this week. That's this one if you want to have a look. But actually, it turns out one of the things in here we already optimized yesterday, but we can have a look at that. And then I'll pull up some fresh profiling data as well. Well, also handy for me to have this as links actually. Latest profiling data from production. Ah, perhaps we didn't deploy this. Okay, anyway, we will, oh no, it's a different link. Oops, why can't I? All right, let's get started for today then. So what we're going to be doing today is we're going to be looking at our Flamegraph implementation, the thing that renders the API response from the server that is then transferred to the UI, and the UI renders it. But we're focusing on this part that basically takes some profiling data as input and transforms it into our graph. So let me just, so this is a pretty meta episode because we're going to be using this very same Flamegraph implementation to explore how to improve this Flamegraph implementation. I thought that was kind of a fun thing. Let me make this a little bit larger, and as always, let me know in chat if there's if I should ever make it any larger or smaller or whatever. Also, if the background music is too loud or not loud enough, let me know as well. But yeah, we're going to be looking at optimizing the Flamegraph implementation. And the funny thing is, what we're looking at right now is actually, and if I reload this, exactly what happens in the background here is exactly that implementation itself. So I think that's kind of a fun thing to do. And yeah, basically, we've been working on reworking how we generate these. And long story short, we kind of switched everything away from kind of native Go structs. And we're now using Apache Arrow arrays to represent this data. So Arrow is a pretty cool technology if you're not already familiar with it. Let me pull up the website. So this is kind of an in-memory columnar format, but basically because it's tables, you can basically represent any data that you want. And in this case, we are representing our graph in rows that then have pointers to different rows that are their children, basically. So yeah, the nice thing about Arrow is it's lightning fast to read and write, and so that's why it's kind of a natural choice for us to use for this project as well. And more generally, if you've been following us for a while, our database FrostDB is actually emits Apache Arrow by itself. So that's how the query engine works. And so the really cool thing is going to be in the future is that we'll have everything from we're querying data from our database to we're rendering data in the front end, and it's all going to be in Apache Arrow, and that allows us to squeeze out a ton of performance. So let's kind of dive straight into it. What we can, I already took some profiling data from our production servers and put it up on pprof.me. I put the links already in the chat. If you don't see them, let me know and I can put them into the comments again. But we can see here, generating the Flamegraph is taking some amount of time, and we want to optimize this. So first thing looks like we're going to be wanting to look at this generate Flamegraph arrow record function. So what does this do? Clearly it has a pretty decent amount of flat value by itself, but let's see what else is happening. Okay, so there's some JSON marshalling going on here. Always like to see that. That's definitely a CPU bound operation. We can we can certainly optimize this. And if I remember correctly, I think I have some. If I'm remembering the code correctly. Hello, Harsh. Welcome to the stream. Let us know if there's anything that you're wondering about today's episode, and I'll do my best to answer that. But yeah, we're just walking through the profiling data at the moment. We've already found Json marshalling, which is a CPU-bound operation. We're appending some rows. This might be a little bit more tricky. These look like operations that have to happen. This is basically adding data to the result array. This is the Apache arrow array, as we can see here. So unless we can avoid doing this, there's not going to be much to optimize over there. Let's see what this does. Okay, this seems to be some sort of closure that we're using. Okay, this is also all arrow stuff. So this is going to be rather difficult to optimize, although I will say, I know we're using some, I want to say I saw it in the previous one. We're using some, here we can see it, memo tables. So we're using some dictionaries, and dictionaries in Arrow are, if you have an array and you insert the same value multiple times and you've defined the array to be dictionary encoded, it keeps a second array to deduplicate the values, and then you're only storing a pointer into your dictionary for the actual values. And this isn't actually writing any new data, so we should be able to reuse dictionaries, the dictionary of the input. This is territory that I've never touched before, so we'll see if we go with this one today. I don't know yet. As always, these episodes are entirely improvised. The only thing we do is we try to search for a victim to optimize, and we try live. Whether we end up succeeding or not is always up in the air, and hopefully you as the audience can be helpful a bit. What do we have next here? Map intersection. Okay. Probably too small to kind of have a big one anyway. Let's stick with the ones that are fairly large. Okay, we can see a slice clone here. This is an interesting one. So this is a new package that Go introduced to generically clone any slice. And as we can see, it actually ends up growing the slice multiple times, which is not ideal. We might be able to optimize something here. The interesting thing is, I thought we actually merged something yesterday to optimize this away. Let me pull up this pull request. So I'm curious why this continues to show up in our, here we go. This was the pull request from yesterday. Let me make this a bit larger. And it was exactly this. We replaced the generic version of this copy with a specific version of this copy, and that should be much faster because we're not growing the slice bit by bit, but we're just doing an exact copy. Actually, I have no idea why the generic implementation doesn't do that, but I'm sure there's a good reason for it. It might be like, yeah, I don't know exactly. So yeah, curious why we're still seeing this. Maybe there are other places where we're calling slices.clone. I don't know. Maybe we forgot to update. Maybe it's all it is that we forgot to update the dependency in our production clusters. We're growing a slice again. This is often a CPU bound operation. If we can be smarter about pre-allocating this, that would be interesting. We'll find out where we're actually growing this slice. Map assigning, these tend to be pretty difficult to optimize. Harsh is asking, is the query API gRPC server accepting the data in JSON, or at some point error records are converted to JSON for some reason? Great question. So at the moment, everything is gRPC. So the frontend does a gRPC web request to the backend that processes the query, renders the result to be returned to the frontend, and returns that as gRPC messages. But that means that we definitely have to go at some point and convert Arrow to gRPC. And there are just some aspects of Arrow that are super, super nice that we would like to, continue to keep and not have to lose by converting to gRPC. One really cool thing that one of my coworkers, Thor, has been working on, Arrow has this concept of allocators so that you can exactly control how much a query is allocating, for example. In a multi-tenant system like PolarSignal's Cloud, it's vital that we restrict the blast radius of a single query so that one single query doesn't the entire query infrastructure and ends up in lower availability of the service for others. And so we would lose all of that if we were to convert things back to gRPC. So ultimately, the goal is that we only communicate things as Arrow records in the product, because that allows us to offer much more stability in the system. All right, so we are assigning to a map here. We're iterating over maps, more iterations, and there's a slice byte to string. Sometimes these are easy to optimize, but we can also see this is only about 1%. So I think we should focus on a few of the ones that we've been looking at here. So I think if we can pre-allocate this slice better, that would be interesting. If we can optimize away this, we'll see if it's actually still in the code. This might be, I don't know if we'll get to this today. And then Flamegraph builder append row. What was this? Okay, we're writing Apache Arrow records here as well. So I think we're good. I think this is going to be the one that we're going to be tackling today. We see this has about, makes up about 5%. So I think this is a good one to tackle. I'm actually I think we're gonna need some data to use for benchmarking. So I'm just gonna download some data real quick. It's not gonna be important what's contained in this data, but just to have some example data. All right. I downloaded some data from production. Hopefully that'll be useful. All right, then let's dive right into it. I'm still sharing my browser only, so let's just here we go. All right, so I've made sure that my Parca repository is up to date. Oops, okay, looks like Renovate bot was
busy while in between preparation for this and then starting the stream. All right, so first things first, let's look at where it is. Flamegraph arrow. Are we using slices? Clone. Huh. So there were multiple places. Okay, interesting. Oops. This is why we have profiling data. We thought we did the right thing, and the data proved to us we still missed something. So let's fix that real quick. Copy children. And this one, even though we know this is the right solution, let's first write our benchmark. I think we already do have a benchmark. Yes, here, this is a benchmark, and this produces our old Flamegraph implementation, so let's change this. Editor is a bit sleepy today. All right, there we go. All right. Now, what was this called? It was called benchmark query merge. We'll do our good old trick of matching none of the tests to run and only to run the one benchmark that we're interested in. Oops. And then we'll try to create some statistical significance. And we'll output some CPU profiling data. And we'll run it. All right, so we're producing some baseline data for ourselves here. This is essentially what the implementation was like before our changes. Oh, okay, we're running this with a couple of different, what is this? And what is N used for? Oh, I see. This is for adding more data to this. Okay. We're not actually interested in the query path as much as we are in just the aspect that does the rendering of the response. So maybe we'll actually write a new benchmark for this then. Yeah, let's do that. Let's write a new benchmark. Otherwise, we would see a bunch of noise in this data that we're not interested in. So I'm just opening the tests here to see if there are any tests over here that already include rendering an existing profile, maybe. These are all just, so far it looks like everything's just synthetic data for the tests, for the unit tests, which is
perfect for unit tests, of course. Okay, so then we'll write a new benchmark. Benchmark, Flamegraph, arrow, Flamegraph. And I have this nifty function somewhere that can convert things. So we're in the process of doing some refactorings to, like I said, bring everything into arrow format, but we're not quite ready, not quite done with everything. So I need to use some kind of conversion functionality for this. So here we go. That's our old profile. I feel like we could maybe directly convert a pprof profile. Pprof. Could have sworn we already wrote something to convert pprof profiles. All right, does not look that way. Okay, then we'll go with this. Let's see. We have our query test here. Again, this queries directly from the database, which we're not so interested in. So we'll take this. Somewhere we have to have some functionality to what was this called? I haven't touched this in a while. That here we're converting. This is the new profile to the old profile. This we're not interested in. What? Where is this again? I'm totally blanking right now. I could have sworn we had some functionality that can take like a pprof profile and hold on a sec. Is it? Oh, here we go. This is that. Here we go. Okay, finally. I knew it existed. All right, so pprof profile to symbolized profile. That is already in the new format. And just to make sure pprof profile is the canonical one. Yep, okay. So. We read this file and we then parse it, correct, and then check this error, and we run preprop symbolized to this, and that gives us the new type of profile and potentially an error. And we pass in meta, which we still need to do, and we just saw how to create meta data from a preprop profile. That's this profile. Meta from preprop. Pass in this, and it's in memory profile. And we'll just take the first index. Oops. All right. What's going on here? Profile.meta. Okay, we have got multiple. Let's make this Parca profile. This is profile. All right. Oh, okay. Okay, we need to do something else here. We're using some like slightly more optimized versions in the actual hot path, so we regenerate the protobuf structs in Parca. So we'll do on Marshall. Okay, so we have to do this, then proto profile, and we not quite. Do this, and then we pass this in. Oh. No. Okay. What's this? What's this one? Not enough. It wants. Wait, hold on a second. Meta also needs the sample index. I see. Okay. Here we go. Like this. Our function doesn't use the pprof. Okay. For the sake of saving some time here, what we're going to do is we're going to just parse this thing twice. And we'll do pprof profile dot parse our content. Parse bytes. Parse data. What's an unusual name, I would say. Okay, and now we'll do this. Again, I would probably clean this up later, but for the sake of this stream, we'll do this today. All right, so now what we want to do is Flamegraph. And start with Flamegraph, generate Flamegraph. Arrow. Context background. And we'll just pass in default allocator. This is the allocator that I was talking about at the very start, which is super nice. We'll pass in a nil tracer for now, but we'll need to change this. We'll not pass any aggregates and not trim any data. And this returns 3. All right, undefined generate Flamegraph. All right, here we go. We'll still need to get a tracer. That was which argument? It's the third argument here. All right, so hopefully this works. We want to reset this, and now our benchmark. Wrong wire type for field mapping. I know why this is happening. We are parsing, whoops. This thing is actually gzip, and when we look at this thing, it actually does that. So we can do that. All right. Content. No. All right. Let's begin. All right. We've got our baseline. Okay, so let's upload that. That automatically opens my browser, but you did not see that because I'm not sharing my entire screen. So let's fix that. Now you're seeing the whole screen, and we can see this is good. This looks pretty much similar to what we were seeing before, although I will say we're not seeing in this particular. All right, interesting. Here we're not seeing the same data. So what I'm going to do is, in the very beginning, we downloaded some data from production, and we're going to use that as input for our say it was something like this. Let's just double check that. You can see I have downloaded a lot of profiles. Okay, looks like it's 41, not 41 is the latest one. See if this is any different. Oh, this is pretty significantly different, as we can see. Up here, we could generate 32 at a much faster rate. Okay, let's try this again. Okay, wow. Okay, we can definitely see JSON marshalling much more over here. Okay. All right. I guess that decides it, right? I think this is what we're gonna want to look at. And this is interesting because basically this is a fairly new functionality that we don't see over here right now. So let me, I need to do this in a separate tab first. I'm just pulling up some data here. All right, now I can pull this over here. So we can see over here, we've got this thread name label. These are profiling labels where we can distinguish the same stacks by adding, in pprof, they're called just labels, but we generalize them as just profiling labels in the product. And these ultimately get marshaled as JSON so that then the front end can just unmarshal it and easily display these. If we go lower, let's maybe click a specific sample. We should, oh yeah, here we go. We see not just the thread name, but we also see the thread ID. So that's kind of what we're looking at here. I'm glad that worked. I'm sorry that that worked with the production system, and we could see this data. So where is JSON.marshal being called? Okay, so what's important to know here, and is this is the only time we're ever calling JSON marshal. And we're always calling it on these maps that we've intersected before. And we know for a fact we are always going to marshal something that looks like string to a string, right? So my theory is we can replace this with a more specialized version of JSON marshal that should be much faster. So let's see if that's true. Let's see what this thing actually does to marshal. We can see, okay, it's using reflection. It does some iterations. Okay, I feel like, okay, it's doing some sorting, interesting. I don't know if that's maybe a JSON thing. And encodes it. Okay, so my theory is we can probably optimize away a bunch of all of this, doing two things. One, this probably does a whole lot of stuff that we don't actually need. And two, this does a bunch of really small memory allocations, if I'm seeing this correctly. And so because of because we know exactly the type that we're going to be working with, I think we can pre-allocate the slice very exactly so that we don't do these tiny memory allocations that are very expensive overall. We can just do one allocation for the whole buffer and then write the result into it. Now, we want to make sure that we're actually producing real JSON. So let's see, what can we do to ensure that? Of course, we could check the standard library implementation of sorry. We could check the standard library implementation of JSON so that we can see how to do this. There are some like high performance JSON libraries in Go, so like full-length fast JSON Marshall. Looks like I've even read some articles about this. I feel like there's another one. It's called like Easy JSON or something like this. Yeah, okay, yeah, that's the one that I've seen before. Okay, let's look at these three implementations, I would say. Maybe all we need to do is replace this thing. Does this thing have some benchmarks? Yeah, okay, cool. What are we looking at here? Encoding. So this is Go CCY, Go JSON. Okay. We have a small struct. So this is probably the most representative one for us. I mean, judging by these benchmarks, sounds like we should be using this one, but it doesn't appear to be comparing to this one, fast JSON. I now wonder, can we just, let's cheat a little bit and we'll just we'll do a single iteration. All right, so it's just something, okay, doesn't really matter then. Okay, that's helpful. So it's just like two entries, and so what we can do is we can write another micro benchmark that just benchmarks marshalling our map. So benchmark marshal map. So we have our map, string, test1, test2, something else. And now we probably this doesn't really make much of a difference, but yeah, we do this and we'll see what we get. All right, so this is already not too bad, but I would say let's yeah, let's write a couple of these. So we do b dot run something like this. Yeah. Lib. Yeah, okay, cool. That's good. Now let's test that against, what is it called? Let's just try all of these. We'll test it exactly for our use case, not for the benchmarks that they've given us. We want to know the truth for our workload. So go CCY JSON. Is this drop in, or is there a faster API? I don't actually care about compatibility with the. Okay, so we can do some buffer reuse here. That's already pretty good. I like that. No escape. Okay, let's read this documentation. Therefore, so JSON Marshal and JSON unMarshal receive interface value and they perform type determination dynamically to process. In the normal case, you need to use the reflect library to determine the type dynamically, but since reflect.type is defined as interface, when you call the method of reflect.type, the reflect argument is escaped. Therefore, the arguments for Marshal and unMarshal are always escape to heap. Ah, I see. Okay. Okay, so this is about making something not escape to heap. That's interesting. Therefore, so what does this do initially? It was okay. Okay, I see. So they re-implemented some reflection functionality to make this faster. That makes sense. No, let's understand. Change direction. Okay, encode test. Okay. All right, I guess it's just .marshal, okay? Go CCY. we got our standard lib one. All right, that's already cutting it in half just by using a different library. That's definitely a huge win, but now I want to know. Now I want to know. Fast JSON. Yes, I can't not use Vim anymore. I'm too used to it now. All right, so okay. That's Marshall. Let's see if this works. Obviously. Okay. Okay, so we need to do something like writer okay, we need to do I'm fast JSON. I mean, I like the look of that already. Let's see if we can get even better. We'll try easy JSON as well, even though they tell us in their benchmarks that their thing is faster. All right. Let's see if fast JSON is the fastest JSON. All right, oh wow, it's slower than the standard lib one. I suppose that's at least in part because they want to reuse this writer, I think. All right, looks like Go CCY JSON is leading so far. Let's, last but not least, try easy JSON. And this has, okay, it's also compatible with all right. Easy JSON does not look, it looks like we would have to Did they compare themselves to FFJSON here as well? Hello. Interesting. Maybe they only compared themselves against libraries that they're good against. FFJSON, let's see. Harsh was saying that slightly curious to look at the memory profiles for these as well. You're absolutely right. That is also an interesting aspect of this. Oh, okay, this is so old. I think I'm not gonna touch this. I feel like we would just burn ourselves here, and it says that marshalling is 2 to 3 times faster than coding JSON. Okay. What's SIMD JSON? Okay. Okay, this only does unmarshalling. Shame. This is the thing we are not interested in. All right. I want to give EasyJSON one more chance. Data EasyJSON test. Yeah, it doesn't even have a Go mod. Yeah. Okay, so large struct. What is large struct? How's this thing defined? Data, I assume. Okay, I think this thing requires that you. What's this? I feel like this thing requires some sort of compatibility. It doesn't seem to be very easy to use. Okay. I'm gonna go with this then, and well, Go CCY JSON was definitely our winner. So let's go back to this and let's look at some profiling data. So I only wanna run this one this time, and we'll run a couple of iterations. Actually, let's fulfill your wish and look at memory profiling as well. So we'll get that uploaded. So okay, we don't care about that. All right, so there are some allocations happening here. Append map key value. Okay, interesting. New map context, release map context, append string. Append normalized HTML string. Map iteration. Okay, the map iteration we're not gonna get around. Why are all of these things sorting? Is sorting part of the JSON specification? Okay, this is just an ES5 specification. Let's dive into that code. Go ccy vm.run in internal encoder vm.go. All right. Internal encoder vm go. And this was on line what? We call sort, okay. Does anybody know in chat maybe? Is sorting part of the... I'm baffled. I didn't think that would be a thing. Up map end. Up map value. But none of these, and let's check the profiling data. Maybe it does pre-allocate. Ah, this is because it's using a pool probably. So the first iteration might be pretty expensive. Okay. Okay, so we've already got it to be fast. It's about half of what it was before, just by changing the library. I say let's take it a level further and try to only implement marshalling a string-to-string map. And to do that, we'll write a function marshal string map. That does the equivalent of this. And basically something like this. Let's see. We'll do this iteratively. Counter. Separately Json string is this? That we wanna. And then we do like this. And this. This is probably at this stage quite a bit worse, but we'll still give it a shot. I guess at this point we only really need to compare the CCY and ours. We'll want to do both again. Okay, fast as it was before. Ooh, ours is worse than standard lib. Okay, that's harsh. All right, we'll need to work on that, but I'm confident that we can figure that out. Let's have a look at the profiling data. So, all right, so most of it is that we're wildly this is unsurprising that this is all really expensive here. So half of the time we're just doing really expensive stuff that we shouldn't be doing. So one good news is we can just pre-allocate some memory, and for now we'll just say just do this. Yeah, that. The other one was returning a byte slice anyway, so we'll just do the same thing. Okay, so hello, Nicholas. Welcome back. Okay, we're still not doing too well with this one. How's your Friday going, Nicholas? So we're converting, what are we converting to a string? What? Let's So Nicholas asking in chat how the session's going so far. So we have successfully optimized something by 50%, but that was basically just by replacing the Go standard lib JSON implementation with a faster alternative that cut it roughly in half. But I feel like it must be possible that we have a more specialized implementation, because all we always want to marshal to JSON in this very specific case is a map from a string to a string. So I feel like this should be very, very simple, very cheap to do. So I'm trying to write an even faster implementation over here that specializes only in that, only solving this one case, not the generic case. But it's not going too well so far. But let's see. So we were looking at this faster implementation called Go CCY Go JSON, and I would like to here's unordered map. So something that we kept seeing in all of the profiling data, here I think it is, oh, this was ours, was for some reason things keep getting sorted all over the place. And sorting, as we all know, is a fairly expensive operation, but it now looks like, whoops, now where did I go? It now looks like there are some options for unordered things. But again, let's try to implement our own that we can make much faster. I just want to find wherever this thing marshals a string. Wait, we saw that in the profiling data, I think. Append string, internal encoder append string. Append string, all right, here we go. All right, append normalized HTML string. Okay, so this appends to a buffer, which we already have. That's good. Okay, and this also takes care of quoting. Okay, and it also does an empty quote. Okay, good, good, good. We like that. Okay. Normalized HTML string and HTML string, append string. What's append string? I just wanna see the simplest possible option. Let's try it. Let's try just doing this. Taken from, before we do something like this, let's have a quick look at the license. All right, MIT license, amazing. Go CCY. So now, what we'll do is we'll replace all of this with and string. So some string to uint64 slice. Oops, didn't too far here. All right. Need escape. What is that? Oops. Okay. Good. This makes sense. All right, let's try this. That's another table for us here. Hex table or something. Maybe it's a function. Undefined hex 146. Oh. Let's go back. There we go. All right, we're getting closer. We are getting closer. That's good. There was actually, let's look at the profiling data. It's almost all of it is making the slice now. Okay, we're getting there. The other library was cheating. It was reusing slices. So that is something that we can do as well. So we'll do this. Instead. Reset it on every use. We'll pass it in. We don't care about being compatible, right? We control all of this code. All right, yeah, we are faster than the optimized version. I don't know if you remember, but we test it here. So remember, this was 50%-ish better, and we're another 100 nanoseconds, 130 nanoseconds faster. All right, nice. Very satisfied with that. Now, let's ours again. And I just realized that I kept writing it into old.txt. Not what I wanted, but it'll do today. So let's look at the profiling data again. Map iteration. I highly doubt. Nicholas is asking, are we gonna see a release today? I think probably not, but this is definitely gonna be in the next release of Parca, for sure. Duff 0, but yeah, that's the almost nothing. Map iteration. I feel like the only way that we're gonna make this better is by not using maps. And then we're potentially defeating the purpose. Let's see, append string to, yeah, that was all right. I mean, I think we've done pretty well already today, but let's just give this a last look by using some functionality that unfortunately Polar Signals does not implement yet. We are working on it. We'll start with this one. So, I mean, looks like there's not going to be much that we can do here. I wonder if there's something we can do with branching here. If we can remove this branch, we may be able to improve the overall performance of this. Nah, probably not, because most of the logic happens in append string. So let's have a look. Nah, this all looks like very simple operations. I would say let's give this a cool, just so we can have our wonderful benchmarking result picture. Let's, this is already ours. So we'll just actually, no, sorry, this thing I don't want to. And Harsh was saying there is a doc in the core JSON schema org that has the word ascending, but not sure it applies here. Can't send links here. No worries. you know, honestly, I think we would just test this with the Parca front end, and if, you know, the front end code is happy with it, then, you know, we're happy with it, I think. That's all right. Okay. Actually, we wanted standard lib as well. Okay, so now. And old is not really old, it's go CCY. Go CCY. Okay. Standard lib. We've got new, but we'll call it new hours. Now, I think you can't do comparisons like that. We need to remove the identifier. So let's just do standard lib and go CQI. Yeah, exactly. That's what I thought. Anybody know if there's a trick to make this comparison actually compare each other? But I think they're technically just different benchmarks, and so it will refuse to compare them. All right, so here we go. Standard lib to go CCY, we've got a 40% improvement. Go CCY to hours, we've got another 35% improvement. And so finally, standard lib to hours is a whooping 61% improvement. I'm pretty happy with that. So let's commit. No, don't really want to commit. What we're gonna do is we're gonna throw out go CCY now again. Where did we write this test? Flamegraph. I'll throw this out again, because then we can go check out. All right. Just to be sure though, make sure there's nothing dangling around here. Right. Let's also undo this change. We didn't actually need this. Okay. Now, fast map. At fast string strings based on our showing. And now I do want to try if we can still squeeze more performance out of that with branching. I'm gonna be pretty what do you say? Unscientific about this. I just wanna know. I just wanna know if this is gonna work. So we're gonna extract the keys. I'm pretty sure this is not gonna outweigh the benefits, but we'll see. So, so we've got the keys, and we're gonna iterate over the keys instead, and do this. And what we're gonna do is this, because then we can always do this. 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 Well, maybe this will actually work. And we then do a final count string. Now we have no branching in this function. Again, I highly doubt that this is going to be any better, but we'll give it a shot. $276. What did we have before? Yeah, no, that's slower. And I'm pretty sure it's allocating this thing. That's slow. Is there something clever that we can do here? If I'm trying to do is I'm trying to get this not to go on heap. Let's see. A little better. But ultimately, making this slice is probably rather expensive. Is there a limit? Is there a limit? All right. I'm glad I committed. Why? Oh no! I committed everything except for the thing that was actually important. Ah! All right. Not a big deal though. I actually see an opportunity to still get this to be branchless. I didn't realize this before. We're actually always going to do this, but yes, we're going to do this instead. Again, no clue if this is going to be any faster, but it's now branchless and simpler. So basically what we're doing is we're always going to write that last comma, but once we're done, we're actually going to overwrite that comma again with the closing bracket. So let's see. It made no difference. It looks like so I like this. Oh, that is exactly what I didn't want to do. I still like this code better, so we'll still keep this. Looks like actually it's a tad faster. We had pretty much exactly 61% before, so it's a little faster. Not a huge amount different, but it is actually a tad faster. So this time, let's actually make sure that we get this. And then right now the moment of truth. How much faster have we actually made the main benchmark? Here we go. This is new. Generate it 5 times. Wait, did we actually change? No, we didn't. So this is old. We didn't actually change the implementation used. So fix that. The signature again. So let's do 512 by default. Yeah, introspection, and just so we call this thing exactly the same as it was before. But We don't actually have this anymore. That's also a nice side effect. All right, so, oh, okay, we can reuse this. Okay. Yep, I like that. Now, oh. Now we need to actually fix our benchmark as well. 740. Because we're all right. I want to say that's looking promising. All right. We have made our Flamegraph implementation about 30% faster. I think that's a massive win. I actually didn't think we were going to get anything close to that much. So super excited about that. Awesome. Well, that's it for today's episode of Let's Profile. As always, let us know if you have any suggestions of what you want to see being profiled. Again, I've mentioned this a couple of times in the past, but ideally this is something that we actually run in production so that we have some real profiling data that we can use. And yeah, give the video a thumbs up, a like, subscribe to our channel, follow us on Twitter, and then hopefully see you next time. All right, have a good one, everyone. Have a wonderful end of your Friday, and see you next time. Have a wonderful local time.